A geometric sequence is obtained when we multiply the preceding terms by a constant non-zero number. We call that thing the common ratio. We use the variable r to represent it, and it can be found by taking the ratio of any two successive terms. So the second term over the first term, the third term over the second term. For example, here are some geometric sequences. 1, 2, 4, 8, 16, 32. This guy has a common ratio of 2, where each term was multiplied by 2 to generate the next term. A geometric sequence like 1, 1/2, 1/4, 1/8, 1/16, 1/32 has a common ratio where we've divided by the same number, divided by 2 each time, or multiplied by 1/2. So these common ratios can be whole numbers, the numbers can grow, or they can be fractions, and the numbers can shrink as we make the sequence. The point is that we're multiplying by the same number each time. To do that, we generate an nth term, and the nth term of the sequence is the first term, that's starting point. You'll notice that in this previous sequence we had a first term of 1 times the common ratio r to the n minus 1 power. So we had a starting point a1, and then we multiplied by r n minus 1 times. When we're given a1 and r, we can make a formula for the nth term of the geometric sequence. an is a1 times r to the n minus 1. If we know a1 is 8, we have 8 times r, but r is negative 5 to the n minus 1. So this formula here generates the nth term of the geometric sequence. That means we don't have to write out 19 terms to get to the 20th term. We can just jump right there. Notice that this 8 times negative 5 to the n is not negative 40 to the n minus 1. That does not follow proper order of operations, which say that we should do exponents and then multiply. So this n minus 1 is only on the 5, and we cannot multiply 5 times 8. That's a common mistake. If we would like to find the fifth term without making the first 4, it's a1 times r to the 4th power. So the fifth term is a1, which is 8 times r, negative 5 to the 4th power. Negative 5 to the 4th is huge, times 8 makes 5,000. So the fifth term is 5,000. Number 14 comes to us as a sequence. We have to identify a1 and r on our own from the pattern. a1's easy to find. He's the first term. r is the common ratio. What did we do to get from 1/2 to 2/3, from 2/3 to 8/9, from 8/9 to 32/27? If you don't know, if you can't recognize it, or you have no idea with fractions, you can just divide two subsequent terms of the sequence. 2/3 divided by 1/2, for example, is 2/3 times 2 over 1, which is 4/3. We could check it again. What if we take 8/9 and divide it by 2/3? If we did it correctly, we should have the same common ratio. That's 8/9 times 3/2. 3 and 9 share a 3, so there's a 3 down here. 8 and 2 share a 2, so that makes a 4 and a 1. And this common ratio is also 4/3. So that verifies for us that sure enough the common ratio is 4/3. To write the nth term then, we have the first term, 1/2, times the common ratio, 4/3, raised to the n minus 1. That's a general formula for the nth term. And we want to also find the fifth term. That will be 1/2 times 4/3 raised to the 4th power. If we want the fifth term, we do n minus 1 there. And this value is 128 over 81. So to write it nicely, a5 is 128 over 81. So remember the general formula. for any nth term is the first term times r to the n minus 1. We can use that to generate some equations from a2 and a7. For example, the second term says that a1, which we don't know, times r, which we also don't know, to the first power equals -6. And from the seventh term, we realize that a1, that we don't know, times r, that we don't know, but raised to the sixth power equals -192. This is a system of equations that we want to solve. We can use them against each other to solve for a1 and r. You could try elimination here, but they're not added or subtracted to each other, so a substitution will be best since they're non-linear, that this guy is raised to the 6, so like r1 minus r to the 6 doesn't get us very far. So let's say these are equations 1 and 2. Let's solve equation 1 for a1. That gives us that a1r equals -6. So a1 equals -6 over r. Once we've solved one equation for one variable, we can substitute that value into equation 2. So now we have equation 2, a1 r to the 6 equals -192. Well, we can put the value for a1 that we found in there, -6 over r times r to the 6 equals -192. Now we can solve for r. This is r to the 5th on this side equals -192 divided by -6 is 32. So r equals 2, the 5th root of 32. So now we have r. We can go back and solve for a1. The first term, therefore, is -6 divided by 2, which is -3. And now we have those solutions. a1 equals -3, r equals 2. From there, we could write the general term of the equation. We could find any requested term. We can go anywhere from there. Using these formulas in a different way, maybe we want to go back and find the first term when we know the second term and the fifth term. The same thing applies. The same idea is that any nth term is the first term times r to the n minus 1. So we want to write out what do we know. The second term, a2, is 3, which equals a1 times r, which is unknown, to the first power. And the fifth term, a5, is 3 over 164, is a1, which is unknown, times r, also unknown, but to the fourth power. So again, we have the system. a1r equals 3, and a1r to the fourth equals 3/64. Solve the first equation for a1. a1 is 3 over r. Substitute this in the second equation. So equation 2 becomes a1, which is 3 over r, times r to the fourth equals 3 over 64. Simplify this, r cubed on the left equals 1/64. You can take the cube root of both sides to undo the cube and find that r is 1/4. So now that we know r is 1/4, we could go back to find a1. Take this guy, sub him back in over there. a1 equals 3 divided by r. r is 1/4. 3 divided by 1/4 is 3 times 4 over 1. So the first term is 12. It all hinges on this formula and finding your way to what's desired.